Have you ever tried reading an email while someone's talking to you and realized you didn't catch a word they said? Yeah, me too. Most of us stink at multitasking. Our brains slow to a crawl the moment two demanding things collide. But here's the twist. Researchers now think that with the right kind of heavy-duty practice, the brain can learn to run one task on autopilot while you pour full attention into another. In other words, true parallel processing. Intrigued? Let's dig in. First, what actually changes upstairs when a task slips onto autopilot? The key point is that the handoff is physical, not just psychological. Early on, a brand new task lights up the brain's flexible, problem-solving hubs, mostly in the prefrontal cortex. After thousands of reps, control migrates to leaner, faster circuits in sensorimotor areas and the basal ganglia. Think of it like moving an app from your laptop to a dedicated microchip. Same job, way less power. We've seen this story before. Learning a tennis serve, for example, starts messy and frontal lobe heavy. With practice, the movement slides to streamline motor loops farther back in the brain. The new research says the same offloading can free up enough cognitive space that a second, still tricky task can run at the very same time. Now, you might ask, can any routine, drilled long enough, make the jump? Not quite. Evidence so far says tightly defined sensorimotor tasks, things with clear, repeatable input-output rules, transition most easily. Abstract reasoning, with its "it depends" vibe, resists compression. Behind the scenes, plasticity tools like synaptic pruning and myelination carve out what are basically neural fast lanes, but only for task families that cooperate. Here's where the science gets hands-on. A Georgetown team set up a classic dual-task challenge. Participants had to make a tricky visual decision while also hitting specific keys, two unrelated streams that normally jam each other up. At first, reaction times ballooned and error rates spiked. No surprise there. But after tens of thousands of trials, yes, thousands, a subset of volunteers hit a sweet spot. Accuracy stayed high, and the usual reaction time penalty almost vanished even when the two tasks landed at the exact same moment. What did their brains look like? High-resolution fMRI showed a clear redistribution. Late in training, moment-to-moment swings in the prefrontal control network no longer predicted success on the overlearned task. Instead, variance huddled in those lean sensorimotor and basal ganglia circuits. Importantly, the prefrontal cortex didn't go dark. It zoomed in on the still demanding task while the automatic one marched along downstairs. EEG added timing detail. Early on, brainwaves marched in strict serial order. Finish task A, then start task B. Months later, traces overlapped, showing partially independent pipelines firing within a few hundred milliseconds of each other. That overlap is the smoking gun for real parallelism. A quick analogy helps. When you first learn to spot subtle differences in wine, the whole tasting experience floods wide swaths of cortex. With practice, specialized columns and sensory areas pick up flavor notes automatically, leaving higher regions free to ponder vintage and terroir. Same idea here. Compress the basics, free the boss. Now, not everyone cracked the code. People who kept suffering dual task costs showed stubborn coupling between control and sensorimotor areas. So, another open question. Could smarter feedback schedules, or maybe a dash of non-invasive brain stimulation, nudge more learners into the autopilot lane? Stay tuned. Let's ground this in two everyday scenes. Picture an air traffic controller who's drilled emergency checklists so deeply that they run in the background while she scans live radar data. Or think of a seasoned gamer who chain combos complex moves while chatting fluently with friends. In both cases, one heavy stream has been trimmed so lean it barely dents attention, making room for another. Big picture, this research stretches our idea of attention's limits. What once looked like a hard ceiling can, in specific cases, lift if we put in the reps. It also nudges a deeper question. If routines migrate out of conscious control, where exactly is the you in your daily actions? Let that one simmer. Before we wrap, try a little self-experiment this week. Pick two tasks you regularly botch when done together, say, sorting email while updating a spreadsheet or driving while absorbing a podcast. Now, for 5 days, spend 10 focused minutes pairing that exact combo under controlled conditions. Same order, same timing, every session. Track 3 signals: fewer mistakes, less mental fatigue, and quicker completion. You'll have an early read on whether your brain is starting to carve its own fast lane. So here's what we covered today. 1. The brain can, with intense practice, offload a task from flexible prefrontal networks to lean sensorimotor circuits. 2. That offloading opens real parallel processing space, shrinking the usual dual-task bottleneck. 3. Not every task qualifies. Tightly ruled sensorimotor jobs make the jump most easily. Abstract reasoning fights back. 4. In the Georgetown study, thousands of reps rewired brains and behavior. Reaction time costs nearly disappeared, and neural control literally moved downstairs. 5. Individual brains differ, which means training schedules, and maybe future tech, could tilt the odds in your favor. The takeaway? Your attention limits aren't etched in stone. With the right drill, one demanding routine can become light enough that another can slide in beside it. That's a superpower worth exploring. Thanks for listening. Next week, we'll ask whether music training gives similar multitasking boosts, even if you can't carry a tune. Until then, keep an eye on your own dual-task experiments, and remember, practice doesn't just make perfect, it can also make parallel.